Good morning. My name is Dwayne Davis. I'm Tech Support Manager for Associated Research. I'd like to welcome everybody today to our webinar. It's a technical review of ground bond and ground continuity testing. If you have any problems with the presentation relating to the running of the meeting, audio, visual, please address those to Jim Kennedy through our chat line, and he will do his best to assist you to try to get you back up and running. If you have any questions concerning the material that is being presented, please use our Q&A facility, and we will address those to you either back over the Q&A or try to address them during the webinar presentation itself as we go through the material. So with that being said, let's go ahead and get started. We're going to talk first about the why electrical products are grounded. We're going to talk about the different types of grounding systems. Talk about different classifications of products. Class 1, which is a product that has a grounded enclosure or chassis, or a Class 2, which is a either double or reinforced insulated product itself. What is considered to be a good ground as defined by the National Electrical Code? What is a ground continuity test? And what is a ground bond test? Essentially the differences between these two, which is a better test, which is actually preferred. What is specified by the safety standards, and how these tests are actually being performed. So with that, let's go ahead and get started. When we're talking about grounds, we're really talking about two different types of grounds. There's a system or a service ground that is typically where you have one conductor, which is essentially the neutral, that is tied back to ground at the transformer or generator, essentially the service entrance into a building. This type of ground is actually designed to protect machinery, tools, and insulation against damages, due to surges, lightning, this type of stuff. Other equipment grounds are used to where they incorporate an actual third conductor, a grounding conductor in a product, and these are really meant to safeguard the operator against electrical shock should the insulation within the product itself fail, where you now have a short circuit between a hot conductor and any exposed dead metal that could become energized, and that could create a shock hazard because all of our power distribution systems are in fact referenced to ground as defined in our first category up here when we're talking about grounds. Because of all of our power systems are essentially referenced to Earth, the current tries to get back to that source. And one way of protecting any individuals that are handling products is essentially to ground the enclosure of that product so it is at that Earth reference. It also provides another path for the electrical current to flow, which is a low impedance path that should provide protection to the operator by allowing the circuit protection, fuse or circuit breakers, either within the product or within the system, to open up, shutting off power to the device that essentially has a short circuit. So grounds are very important. Unfortunately, they are one of the most commonly defeated safety features that we build into products today. Because of some of the older systems, people will use a two-prong cord to ground a product that is meant to be grounded. They cut off the ground pins of the line cord. They may be just plugging into a outlet if they're in a older home that may not have a ground circuit, but these are some problems and stuff. Okay. Grounding or protecting earthing is really one method that is used to safeguard against electrical shock hazards. As I stated earlier, this is a physical ground connection to earth. The photograph here basically shows a ground rod driven into the earth and a wire tied directly to that ground rod. And that basically is connected back to the distribution panel leading power into the building itself. So this is one method of actually going in and grounding. At every pole or transformer, you'll see out in the, if you're looking at overhead power distribution lines, you'll find, ground wires running down that pole, tying the, the neutral side of the line essentially back to ground, and giving that ground connection and stuff there. Okay. Ground basically is this physical connection to earth. It is at 0 volts. It is what we call our reference. It is there to create a second line of defense in guarding against any electrical shock hazard should the insulation within the product itself fail. This ground circuit connects all conductive exposed parts within a product together, keeping them at this ground reference. So you don't have a difference of potential between two products that are sitting next to each other, so that if you could contact one and contact another, that could create a shock hazard just due to leakage within the product itself, that could put the enclosures of these products at different potentials. Or if the insulation of that product should fail, this ground circuit directs that power back to earth and, as I mentioned earlier, allows the circuit breaker or fuse to open, protecting you against an electrical shock hazard. Yeah, the primary purpose of an electrical ground is to reduce the risk of any serious electrical shock from currents that leak to any exposed parts of the appliance, power tool, other electrical conductors that could create a shock hazard to the operator. It may not necessarily be a short circuit. There could be enough leakage current within the product going to the enclosure of that product that could create a shock hazard. Grounding or earthing is one method of safely routing that leakage current back to earth and guarding you against an electrical shock hazard itself. Grounding or earthing was originally designed as a safety measure, but it has really become essential in today's electronics also to help reduce and eliminate electrical noise that could cause interference in the operation of the equipment and cause the equipment itself to malfunction due to this electrical noise. Could cause a microprocessor to lock up or other issues and stuff similar to that. Could cause the device not to operate properly and therefore creating a shock hazard or some kind of other hazard as a result of it. Okay. What's wrong with this picture? When we're talking about grounds, and yet we manufacture devices that can adapt products, such as this little ground adapter here. You can buy these adapters at almost any hardware store or you know, even the appliance section of a grocery store. You know, you may find one of these little 3-prong to 2-prong adapters. And one thing you'll see, many of these devices either have a wire coming off of them, or got this tab down here that is designed where they tell you to take this, remove the screw from the cover plate, and ground this to this cover plate, or, you know, to the receptacle whenever you're using one of these to provide a ground connection. That it may be a very big fallacy depending upon the outlet that you're plugging your you know, your device into. Many older homes that were built back in the you know, the 1940s, 1950 era, never had ground circuits in the wiring in the house itself. I remember my parents' home was built back in 1942, and the National Electrical Code did not require that any of the wiring actually even be in conduit. You know, it was run on you know, little porcelain insulators. I remember seeing it, you know, in the attic of our house, and then drop down into the wall. And the wire itself wasn't even in conduit. You had both just the hot and the neutral conductor going to a outlet that wasn't even polarized. So you could plug in your plug in either direction, so it would give you the possibility of reversing the polarity of the input to the device that was actually plugged into that outlet. You know, a metal box nailed to a wooden 2x4 does not provide an effective ground path. My parents' refrigerator was a old Philco refrigerator before the days of frost-free freezers, and one of the major things that I recall, actually it was the first time I think that I ever received an electrical shock, I tried to get an ice cube tray out of the freezer, and I found that it was frozen in place just due to the frost and people spilling water as they put the ice cube tray, you know, into the freezer, and you know, if it froze the ice cube tray in place, then it made it difficult to remove it. Easiest way of getting it out would be grab a table knife out of the kitchen sink drawer and jab it underneath the ice cube tray to pop it loose. Just so happened the kitchen sink was, the cabinet was metal, connected to a beautiful grounding system, the water pipe of the house, and if you were, it was in close enough proximity, you could hold on to the handle of the refrigerator and reach over to open up the kitchen drawer and you know, to get a table knife out of the drawer, and there was enough leakage current flowing through the chassis of the refrigerator, going through your body back to the ground, that you got a pretty healthy shock off of it. You know, it got your attention. It, you know, heard all sorts of colorful language from my mom every time that she grabbed a hold of it. You know, us kids kind of thought it was neat. We would invite the neighbor kids over and say, "Here, touch this," and you know, watch their reaction and stuff. But it was enough to give you a nice startle reaction from the shock. My brother came home. He enlisted in the Navy, and he was about, you know, 12 years older than I am, and I remember him, you know, attaching a ground wire to the refrigerator, and that basically eliminated the shock hazard. Once the frame of the refrigerator was tied back to ground, you know, all that current was safely routed back to to ground, and essentially eliminated the shock hazard. So how do grounding systems work in a product itself? Electricity is really designed to travel in a closed loop. Whatever leaves the source is going to try to get back to that source by some means or another, and that power is basically designed to try to run the product or appliance that is connected to it. Over here on this side, we have our power distribution transformer. Kind of shows the secondary coil of a transformer. Feeds into a circuit breaker in the cabinet. Coming out of the circuit breaker, this is our hot conductor going into our product that is going to be connected to this outlet, or to this line to run our product. The return circuit of this product basically would be on our neutral, and this basically flows back in our neutral conductor and to the secondary side of the transformer. Notice it's also connected to earth ground here, okay? So we got our nice ground connection setting here, tying this neutral back to ground here, giving us our grounded neutral return conductor. Okay. If this were in the home, like my parents' house, and this was our refrigerator, and if it did not have the ground circuit, you could have enough leakage current essentially flowing in that product itself that this leakage current basically would flow through whatever insulation resistance, capacitance and stuff, to the frame of the refrigerator, and as soon as you came in contact with this metal enclosure of the refrigerator and ground, you could receive an electrical shock even if there wasn't a fault within the appliance itself. This product could continue to operate. If the thing was faulted and there wasn't enough leakage current flowing back through that would cause this fuse or circuit breaker to open up, this product could continue to run. And one thing to keep in mind, your body runs on electrical impulses, and you have electricity running through your body, it's going to affect the way your body functions. Can cause your heart to go into fibrillation, can cause respiratory failure, make it difficult, for you to breathe, can cause physical burns, nerve damage, depending upon how much current actually flows through your body, the duration for that current flow, your physical condition and response, all this stuff comes into play. If you come in contact with this product and you yourself are connected to ground, whatever this ground path is, you're going to have electrical current flowing through your body, and it's going to could be potentially lethal as a result of that current flow. It could cause your heart to go into fibrillation, and could basically end up killing you. Okay. This ground circuit that we have in our product, it is designed to provide a low impedance path for this current to flow back to earth, and it takes the enclosure of that product and ties it back to ground. Okay, this whole enclosure. Okay, and if it is in fact grounded, then this current flowing will flow from this fault back to earth ground, and the enclosure is essentially going to be at 0 volts, So the end result is you're not going to end up getting a electrical shock as a result of this current flow going back through your body. So this ground circuit, having a low enough impedance path, will allow enough current to flow in this circuit, causing this fuse or circuit breaker to open up. End result, killing power to the appliance and protecting you against any severe shock hazard itself as a result of this. So this ground circuit is important. Using one of those adapters eliminates, or cutting off a ground pin basically removes one of these major safety devices that are used to protect you against an electrical shock hazard. And the first protection device is the insulation within the wiring or the product itself. The second level of protection, which would in this case be, if it does have a ground circuit, would be the grounded metal enclosure of the product to guard you against any electrical shock hazards. Okay. What's the National Electrical Code state? NEC 250-45 states that any exposed non-current carrying metal parts of cord and plug connected equipment which may become energized shall be grounded. There is an exception to this. It actually states that any listed tools and listed appliances be protected by a system of double insulation or its equivalent. They shall not be required to be grounded. Okay, if it has this system of double insulation, it is not required to be grounded. Where such a system is employed, the equipment shall be distinctively marked, and following are some examples of the types of equipment which could fall under this category. And it gives some examples saying refrigerators, freezers, air conditioners, clothes washing machines, clothes drying machines, dishwashing machines, sump pumps, electrical aquarium equipment, handheld motor-operated tools, appliances used in damp or wet location, or by employees standing on ground or metal floors. Okay. So it's a pretty broad spectrum of different types of products that require to be either grounded or be protected by a system of double insulation to guard against an electrical shock. So what they're requiring is 2 levels of protection should the basic insulation of the product actually fail. And so there is a backup to guard against any electrical shock hazards. One thing that is kind of common is many of these products are something that is used in a wet type application or could have water and stuff involved in them, or something that would have a pretty good direct contact with the individual using the product itself, such as handheld motor-operated tools. If you're holding on to a product, you've got a pretty good grasp on that, and if that insulation should fail, the odds are pretty decent that you're going to receive an electrical shock unless you have that second level of protection, either the ground system itself or the system of double insulation. I don't know when the last time you looked at handheld motor-operated tools such as an electric drill. You go into a hardware store, you try to find, of course, many of the products now are battery operated, but if you're looking at something that is not battery operated, it runs off of line power, it's very difficult to try to find a handheld tool such as a drill that has a ground circuit. Most of the products today are protected by double insulation, And a big reason for that is because it is probably the most common defeated safety feature that is built within the product today that the operator can eliminate very easily. So it's kind of there to protect us against ourselves from our own stupidity, from not using a product the way it's actually designed to be used. Okay. Why are some products grounded and others not? National Electrical Code basically says that you must have 2 levels of protection to ensure operator safety. A Class 1 product essentially employs basic insulation, and any exposed dead metal of the product must be connected to earth ground. In a Class 2 product, the product employs the basic insulation or functional insulation of the product, as well as a supplementary or reinforced insulation to guard against electrical shock hazards. So, we must have one of these type 2 devices to guard against electrical shock hazards, to protect the operator against these electrical shocks. What is considered to be a good ground? NEC 250-51 states that electrical equipment shall have an effective ground path, which is permanent and continuous. It shall have the capacity to conduct any fault current that is likely to be imposed on it, and a sufficiently low enough impedance to limit the voltage to ground and to facilitate the operation of any circuit protection device. So what are we actually talking about? That ground circuit must have essentially a large enough conductor to be able to handle any fault current that could be imposed upon it, so that ground circuit does not act like a fuse. Its impedance must be low enough to limit the voltage to ground, so there's no voltage drop in that circuit that would allow the chassis of the item to elevate in voltage to cause a shock hazard. And it's got to have a low enough impedance to allow enough current to flow to let the fuse or circuit breaker blow. Okay. If we're talking about a 115 volt product, okay, let's just use an example. I'm going to back up a few slides here. Yeah, we'll use this diagram here. Let me eliminate some of the stuff that I've got drawn here. But as an example, this circuit breaker that we have here, if this is a 115 volt circuit, if we're talking household circuits and fuses and circuit breakers, this circuit could employ either a 15 or 20 amp circuit feeding power into the receptacle, into our that we could plug our products into. Okay, so most bedroom receptacles are probably on a 15 amp circuit. Kitchen, utility rooms might be on a 20 amp circuit. Many of these circuit breakers are what we call a time delay fuse or circuit breaker. And why are they employed? Today, in the many of our products use electrical motors. And an electrical motor, in order for it to start, it requires a lot more force or effort to finally get it to start to move or to turn. Okay, so it requires a lot more current. It's like if you try to push a car. Okay, it takes a lot of force initially to get it to, start moving, but once it's moving, it doesn't seem like it requires as much effort, to keep it moving. Electricity is kind of the same way. In order to get that motor to initially start to turn, it requires a lot more current to, get it to start turning. Therefore, we have time delay fuses and circuit breakers. And what these are designed for, it's designed for like a motor start application where it will allow more current to flow through this device for a short period of time to allow that motor to start to turn before this fuse or circuit breaker opens. There's also fast-acting type fuses and breakers that don't have that type of protection, but they're designed for a little bit different application. But most of your breakers in your home are a type of a breaker that does have some kind of a time delay, in these type devices. So they will allow a certain amount of overload for a given period of time. I looked at some of the specs on some of these breakers, and they can allow up to a 200% overload for up to 2 minutes and still be within specification. So if you have a 15 or a 20 amp breaker, it can carry 30 amps of current for 2 minutes or 40 amps of current for 2 minutes and still be within spec. So this ground circuit that I have here in my product, okay, or in my house wiring, okay, has got, and within the product itself, in both cases, must be capable of handling this overload for this given period of time and not act like a fuse. You don't want the ground circuit to open up, okay? So it's got to be a low enough impedance to allow enough current to flow to cause this fuse or circuit breaker to open up. Ohm's law. Okay. Ohm's law is voltage is equal to current times resistance. Okay. In order to have the fuse or circuit breaker, to open up, let's say if this is a 15 amp breaker, it can carry 30 amps of current, okay, for 2 minutes. If we take that 30 amps, divide it into 120 volts, you'll see that it goes into it 4 times, okay? So what does that mean? That means that my resistance of this ground circuit cannot be greater than 4 ohms, otherwise it will never allow enough current to flow to allow my fuse or circuit breaker to open up. So right away that gives me an idea as far as what this maximum resistance of my ground circuit has to be less than. If it's greater than 4 ohms, then it's my fuse or circuit breaker will never open up. One thing to keep in mind, fuses and circuit breakers are not designed for shock protection. They are designed for fire protection. So if we're relying on this fuse or circuit breaker to help protect us against electrical shock hazards, forget about it, okay? It is not meant for that function. But, it is designed to open up this circuit to prevent some type of a fire hazard and stuff. If you do have an adequate ground, it should protect you, that ground circuit should protect you against an electrical shock should a, fault happen on it. That would, keep the voltage low enough to guard you against any electrical shock hazards. But if this resistance is higher than 4 ohms, it's never going to allow for this fuse or circuit breaker to open up to protect you against, an electrical shock hazard. So that's a problem. Okay. Many safety standards, okay, if you're testing a Class 1 product and you have that product listed by a third party, a safety agency, such as Underwriters Laboratory. Okay. Underwriters Laboratory writes many of the safety standards for different types of products. Today, they kind of utilize and modify some of the harmonized standards that are used so your product is, basically more for a global market than something that may be used in the U.S. only. Okay, but they have national deviations because our National Electrical Code is in fact different than what the code is in Europe or Canada or other areas and stuff. But a lot of the old UL standards still specify that a ground continuity test be done as a routine production line test on every product that you manufacture that is a Class 1 product. So if it has a ground circuit, you are required to test every product with any type of an indicating device, such as a battery buzzer or the like, according to this standard, to determine compliance with the ground continuity requirement. Okay, so I'm reading this section right here. Many UL standards allow indicating devices, ohm meter, battery buzzer, combination or the like, may be used to determine compliance with the ground continuity requirement, but they do not specify a maximum resistance. Okay, so here is where we kind of get into trouble on a simple continuity test. The ground continuity test, you could have one strand of your wire making contact and still pass a simple continuity test, because this is not a high current test. It is not testing for a maximum resistance of this ground circuit. Okay, so a continuity test is in fact better than not testing at all, but it is not necessarily the best test to actually be done on your product to make sure that that ground conductor is intact. Okay, but the device under test, any product, your Class 1 product, must be tested for continuity between the ground blade of the attachment plug and any dead metal parts of the appliance that are required to be grounded. Okay, this is a commonly specified routine production line test that must be done on your product. Okay. Many of the safety standards today that are harmonized actually are requiring a maximum resistance for this continuity test to be 0.1 ohms. So they are getting better. Some of them specify a test current, some do not. Most of the type test standards actually specify a ground bond test versus a continuity test. And what is the difference between a ground bond test and a ground continuity test? A continuity test is really just testing for the presence of the ground. It is not testing for the maximum resistance, nor is it testing to make sure that the ground circuit has the capacity to conduct the fault current that is required, should a fault fail, okay, within the product. Or the ground bond test is a test that is actually done that kind of verifies both of those functions. How does it do that? The ground bond test essentially is a high current test that injects a high current through the ground conductor of your product, okay, through this ground circuit to the exposed dead metal are the chassis of your product itself, okay? So we apply a high current source over here to the ground pin of the attachment plug, okay? And that current flows through the ground wire, through the chassis of the item, and then back into our ground bond tester. We have a what we call a Kelvin type setup that what this is essentially is a 4-wire measurement type circuit where we apply the current through one conductor and we monitor the voltage drop through another conductor. And essentially what this does, it eliminates the resistance of our test leads in our circuit, okay? So this is no longer included in the measurement. So whenever we do a ground bond test with one of our products that, employs a Kelvin system, we're actually measuring the resistance from either the ground blade of the attachment plug, wherever it is being made, connected to our adapter box or to our product, or if you have a removable line cord from the receptacle that, that line cord plugs into. You make that measurement from that point to the chassis or dead metal on the product to measure the resistance of this ground circuit. What test is this done at? What test potential? How much current is employed in going through and doing this test? Okay. You have to follow the safety standards. The standards itself dictate typically that this test be done at a potential, most standards say 12 volts or less, okay? So it's either 12 volts or less as far as the output potential, open circuit potential that is actually be applied. Some standards say 6 volts or less if you're talking a medical product. And how much current is applied? Many standards basically state 2 times the current capacity of the attachment plug, okay? So if this plug here can plug into a 15 or 20 amp receptacle, if it can be plugged into a 20 amp receptacle, it's 2 times the 20 amps or a 40 amp test or if the product is fused, it's 2 times the fuse rating of the product itself, okay? So if your product is fused, it's 2 times the fuse rating. If it's not fused and you're relying on the fuse or circuit breaker of the circuit that your product is plugged into for the protection, then it's 2 times the attachment plug capacity. How long is this test done? As a type test, they are, again, simulating the specs for a time delayed fuse. It's done for 2 minutes or 120 seconds. So you apply a high current test through this ground circuit for 2 minutes, and the resistance of this circuit, if your cord is included in the measurement, it is typically less than 0.2 ohms. If your cord is not included in the measurement and you're going from the receptacle, it's normally less than 0.1 ohms as far as the maximum resistance of this circuit. Okay. So the ground bond test is different from the continuity test in that it is testing the integrity of this ground circuit to be able to handle any fault current that could be imposed on your product should the insulation of the product actually fail. Okay. Let's look at the safety standards just to kind of verify this. UL 60950 is the safety standard written by Underwriters Laboratory for information technology equipment. As a type test, what is a type test? A type test is a design or a test that is done by the safety agencies when you submit your product to the safety agency for an approval for a safety listing. Okay, so one of the tests that they would perform on the product is this ground bond test. Okay, so under this standard, it says the test current is 2 times the current rating of the circuit under test. Test voltage is not to exceed 12 volts, and the duration of the test is 120 seconds. The resistance of the protective bonding conductor is calculated from the voltage drop. It shall not exceed 0.1 ohms, and this is based upon a 20 amp branch circuit. So if your product can be plugged into a 20 amp receptacle, the test current would be a 40 amp test. Okay. If your product is fused, then you're talking about a different set of parameters. It is 2 times the fuse rating of your product. So if I am building a product that's got a 6 amp fuse in it, 2 times the 6 amp would be 12 amps. That would be the ground bond test, for my product. If it did have an internal fuse, it's 2 times the fuse rating of that product itself for the 120-second duration. Okay. As a routine production line test, how does this differ from the type test requirements? Okay. Many standards, there are some differences between a routine test and a type test that is done on your product. EN 50116 is the European norm standard for information technology equipment. Same type, we're talking information technology here under 60950. Here we're talking EN 50116, again for information technology equipment, same standard. Okay. This standard specifies the ground terminal of the earthing contact may not exceed 0.1 ohms, and here they're talking 1.5 times the current carrying capacity of any hazardous circuit is applied, not more than 25 amps, either AC or DC. Okay. This standard didn't necessarily specify AC, but in fact it does kind of, some of the standards do specify at the rated frequency. Okay. So it is a AC ground bond test. Some standards say AC or DC. There are other standards that basically state DC only. Okay, if you're talking something like solar panels, the ground bond test is specified as a DC test there. Okay. Okay, for a time required to obtain a meaningful reading. Boy, if that isn't ambiguous, I don't know what is. So you went from a 2-minute test here to a time required to obtain a meaningful reading. In a production line situation, that's about 0.1 seconds, I think, but that's really not realistic. Whenever you're doing a ground bond test, it does take a little bit of time for that circuit to heat up. That could cause a failure. I normally recommend a ground bond test to be performed for usually about a 5-second period. How did I come up with that? One good test to kind of demonstrate a ground bond test is take a paper clip, standard small paper clip, connect it up to your ground bond tester, and do a ground bond test on it. You pump 30 amps of current for it with a 200 milliohm maximum resistance. It takes about 3 to 4 seconds for that paper clip to turn red hot and fail. And, kind of based upon that, I would say, if it takes that long to melt a paper clip and cause a failure, probably a 1-second test is not sufficient enough to, test that ground circuit. You know, I normally recommend a 5-second test just to kind of give you an adequate time to test that circuit. If you do try to do that test, a word of warning, that paper clip will turn red hot. It may melt and drop down onto whatever is underneath of it. If it is a carpet, be prepared. You will set that carpet on fire, speaking from experience. You know, you could burn the hole in a top of a conference room table. That's not very good either in doing demos and stuff. So don't use a cup of water if a cup is styrofoam, because it will just melt the styrofoam cup as the paper clip goes right through. Now, not only do you have molten metal, but you also have a puddle of water on the floor as all the water goes out of the cup. Anyway, CSA, Canadian Standards Association 22.2, number 0.4, 04, bonding of electrical equipment. For cord-connected equipment, twice the rating of the attachment plug capacity, not less than 40 amps at a frequency of 60 hertz. A measured voltage drop shall not exceed 4 volts. And here they're telling you what the voltage drop is rather than the resistance and calculating the value. They just kind of shortcut it and just come right out and say, hey, you know, the voltage drop shall not exceed 4 volts, you know, based upon that current flow. For equipment with permanent connections to the supply, twice the rating of the fuse is required for branch circuits up to 250 amps. So this is a requirement based upon Canadian Standards Association test. Why 2 times the fuse rating? The ground bond test is performed to make sure that the ground circuit of the product is adequate, that it is capable of providing a low impedance to earth to facilitate the operation of the fuse or circuit protection device. This high current is imposed on the ground conductor to match the requirements for the operation of time-delayed fuses or circuit breakers, which can carry a 200% overload for 2 minutes and still be within specifications. This is the reason why we state that we are talking about 2 times the plug capacity, and the reason for a 2-minute duration, you know, for the test as a type test, actually to verify the design of the instrument itself. Okay. You know, why 2 times the fuse rating? Again, this is you know, part of the requirement and stuff here. Okay, how do these tests differ and which is the preferred test? Ground continuity test is essentially a low current test. It only verifies that the ground connection is present. The maximum resistance is often not specified. So this test is, you know, doesn't really tell me that much. Where the ground bond test is in fact a high current test. It's done at twice the fuse rating of the device, and it verifies that the ground conductor can actually limit the voltage to ground and allow for the circuit protection device of the product actually to function. All right, let's see if we have any questions and stuff. I see one question that came in. It says, if my product is passes the DC, would it pass an AC test? You know, should I use one or the other? Okay. Again, depending upon the safety standards, if you do pass a DC ground bond test, it will most likely pass an AC ground bond test also. There's really doesn't seem to be, you know, much difference in stuff. The AC ground bond test it really is testing for the impedance of the circuit, where a DC test is really just testing the DC resistance. Many of the standards basically stipulate that you test at the operating frequency. So if it's 50 hertz, you test at 50 hertz. If it's 60 hertz, you test at 60 hertz. If it's DC, then they want you to test with DC also. This is very common not only for the ground bond test, but also for like doing a high potential or high pot test on your product. They may want you to test at the actual operating frequency of the product itself. Okay. With that, like I say, we've completed all the material. If you have any other questions, please use our Q&A facility, and we'll try our best. We'll leave it open for a couple more minutes. Jim is posting some stuff on our chat line here. Our webinar has been recorded. It will be available later today on our website. Our website is asresearch.com. Go under Events and Training and Webinars, and then go under the Archives section. And you can view any of the webinars that we've done in the past, I think over the last 2-year period, if I'm not mistaken, or 1.5 years. Essentially, through the beginning of last year. Jim just puts 2 years here. Okay. So it is a good training tool. You can use it, open it up at your leisure, and if somebody has not had the chance to review some of the material and stuff, it's a good way of going through and doing that. If you would like a copy of this presentation emailed to you, please shoot an email to Jim Kennessy at jimk@asresearch.com, and Jim can send that out to you. Our next webinar is April 24th at 10 a.m. Central Standard Time. It is Succeeding in Advanced High Pot Testing Applications. Nick Petrowski will actually be presenting that. Nick or Zayed, I'm not sure which is doing the presentation on that. But we invite you to join us and stuff for that. Any other webinars, we do have our schedule posted on our website, so you can, view what our schedule is for the other webinars and stuff that we have scheduled throughout the remaining of the year. We try to do at least one a month. Some of them are, 2 a month. This one we tried to do last week, and we had some technical difficulties where basically the video presentation went down, so we weren't able to do that, so we reshot it this week and re-recorded it. So again, thank you for joining us. I don't see any other questions that have come across. If you do have other questions, please use our info@asresearch.com. You can email that, and we will do our best to get right back to you and come up with some answers and stuff for you, concerning the applications and stuff of your product. Thank you, and looking forward to seeing you guys at our next webinar and stuff.